So oxidation and reduction should be familiar words to you. There is an entire module associated with electrochemistry. The first couple of videos in that are all about oxidation reduction in general, and I strongly suggest that you've watched that before you start this bit. Anyway, oxidation. The simplest definition of it is where something gains oxygen. Thus, for example, we see here where we have a molecule that starts off with one oxygen, ends up with two oxygens. It has been oxidized. The opposite of oxidation is reduction. And so if we look at that same definition but flipped it, reduction, loss of oxygen, and so the flip of that molecule with two oxygens goes to a molecule with one oxygen. Another early definition of oxidation is loss of hydrogen. Thus, for example, molecule with 6 hydrogen atoms goes to a molecule with 4 hydrogen atoms. And as you hope you would imagine, reduction therefore can be thought of as gaining of hydrogen. So there we are, 4 hydrogens and going to 6 hydrogens. Now, of course, those are nice definitions, but there are other specific definitions. A much more general definition of oxidation is where something loses electrons. Thus, for example, when a sodium atom becomes a sodium cation, it has been oxidized because it has lost an electron. And reduction, the reverse, where something gains electrons, thus a chlorine molecule going to 2 chloride anions by gaining 2 electrons. Now, this is the really nice general definition, loss of electrons, gain of electrons, and you can see how it works there. How can we apply that idea, though, to these molecular oxidation and reduction? And the answer is that we use something called oxidation numbers, which I like to think of are fake charges. For every atom in a molecule, you assign it a fake charge, an oxidation number, and there's lots of rules for these, but as far as we're concerned with organic chemists, if we got a metal, it's charge, it's a cation, so its oxidation number is the same as its charge. When we see in just about every organic compound a hydrogen, we can say its fake charge is +1, oxygen is -2, halogen's -1, nitrogen -3. And of course, I hope you can see that by and large, these are the charges that you would expect the atoms to have based on the octet rule. So oxygen wants 2 more electrons, so wants to make an anion of -2 by gaining 2 electrons. So its fake charge in a molecule would be -2. Halogens need 1 more electron to get up to an octet, so therefore their fake charge is -1. Nitrogen, 3 electrons to get up to an octet, so its fake charge is -3. So let's apply that for our first oxidation reaction. Okay, so up here we see we've got 2 carbons, we've got 6 hydrogens and an oxygen. Well, each hydrogen is worth 1, so 6 of those is 6. Each oxygen is worth -2, so we got 6 -2 to balance everything out with the fake charges, because you've got to balance it out because this is a neutral molecule. We need the carbon to be -2 each, so that's -2 plus 3 is +1, -2 is -1, +2 +1, -2 is -1, +1 is 0. Okay, again, much more detailed, slow version of this in the first videos in the electrochemistry module. Continuing on, let's see what we've got in the CH3CO2H. Well, again, hydrogen's going to be 1, so we got 4 of those, so that's +4. Oxygen -2, we got 2 of those, so that's -4, well, +4 -4, our carbon must be 0 here. So our hydrogens have stayed the same, oxygens have stayed the same, carbons have gone from an average of -2 to 0. Looking here for the loss of hydrogen 1, each hydrogen is +1, so that's +6, so each carbon must be -3. Going over to the product here, each hydrogen is +1, so that means the carbons must be -2. So what we see in the oxidation, regardless of oxygens or hydrogens or anything, is that the atoms, some atoms in here, have increased in charge, increased in oxidation number, going from -2 to 0 here, going from -3 to -2. So another possible definition of oxidation is the oxidation number becomes more positive, which therefore means for reduction, the oxidation number becomes more negative. Inorganic chemists assign oxidation numbers. It can be extremely useful while studying oxidation and reduction in organic chemistry as well. So inorganic chemists like oxidation numbers. Trouble with oxidation numbers in organic chemistry is it actually loses some information, as we'll see in this slide. CHCl3, no problem, the carbon is +2. Okay, the hydrogen +1, the chlorine's -1 each, that's -3, so the carbon has to be +2 to balance out the charge. When you've got two carbons, though, as the molecule we saw on that last slide in ethanoic acid or acetic acid, the average carbon oxidation number is 0. Now that's losing quite a bit of information. Now, in order to counter the idea of that, some organic chemists have started using something called an oxidation level, which is where you look at the carbon atom in a particular functional group. And oxidation levels can go from 0 to 4. So if we think of an alkane, that starts off as 0. On the other hand, for every extra carbon-carbon bond we have, for every bond to a more electronegative atom, the oxidation level increases by 1. So if alkanes are 0, then each carbon in an alkene is 1. Each carbon in an alkyne is 2 because you've got 2 extra carbon-carbon bonds. A bond to chlorine is +1 to 2 chlorines +2, and so on. So if we look at our two example molecules, we obviously have to think about the bonding here because we need to decide what's bonded to what. So CHCl3, we're looking at this carbon. It bonds to 1, 2, 3 more electronegative atoms, so its oxidation level is 3. Look at acetic acid here, ethanoic acid, carbon 2, pretty boring, but we're only interested in carbons in functional groups. So carbon 1 bonds to 1, 2, 3 electronegative atoms, counting that double bond to oxygen as being to 2 oxygens. So its oxidation level is 3 at C1. Now, having said that, let's go back to our oxidation number ideas and apply the same specific concept of looking at the particularly interesting carbon atoms. Now obviously CHCl3 doesn't really matter too much, but I'll use it as an example. I'm going to look here, I'm going to say, right, well, the carbon is bonded to a hydrogen, right? Well, when it's bonded to a hydrogen, the hydrogen's +1, so the carbon must be -1. So that's -1, remember that for the carbon. But now the carbon is also bonded to 3 chlorines. Well, chlorines are -1, thus in each of these bonds, the carbon must be +1. So we got its -1 from the hydrogen, and then 3 +1s because it bonds to the chlorine, so that makes it +2. Looking now at acetic acid, okay, C2, this carbon is just bonded to 1, 2, 3 hydrogens. Each hydrogen makes it +1, so the carbon must be -1 to balance out each hydrogen's +1. So +1 for the hydrogen there, -1 for the carbon, +1 for the hydrogen, another -1 for the carbon, +1 for the hydrogen, another -1 for the carbon. So C2, because it's bonded to 3 hydrogens, has an oxidation number of -3. Now let's look at the carbon 1. Well, it bonds to an oxygen. This oxygen is going to be -2, so therefore the carbon has to be +2 for that. Now it bonds to this oxygen that also bonds to a hydrogen. Well, the oxygen's -2. Well, one of its -2s is balanced out by the hydrogen to which it's bonded, which means that it just needs carbon 1 to have a +1 to balance out the -1 that's left behind. So carbon 1 has a total oxidation number of 2 and 1, making it 3. The average oxidation number is 0, but you can see that carbon 1, the bit we're interested in, has an oxidation number of 3. Okay, so several things we'll be looking at as we go through studying oxidations. We're also going to look at the oxidation level. We're going to look at the oxidation number and describe an oxidation or a reduction as we see it through both of those lenses.